Hello, this is Robotics Project 1 and 2. We are group number 4. This is Carolynn Ann Rendon, David Hilton, and myself, Alfredo Mere. Alright, we're going to be talking today about the analysis of a slider crank mechanism and how it works, and basically how we took an input given data to calculate the remaining information that we needed to analyze this type of system, and how it's being used today, and maybe give a little more in depth of how may it be used tomorrow. Now, the synthesis of a 4-bar linkage was also one of our responsibilities to do in this project, and it was just based on making a mechanism pass through specific positions, given an input, just calculating for it to pass through them, knowing some just part of it. All right. So, a 1 degree of freedom mechanism is a system that has one input, and from there all the rest will depend on that specific input, may be a length, a velocity, or just an acceleration. All right, and they are widely used because they are easy to design, easy to maintain, and they have been part of our daily lives throughout.
Okay, the slider crank mechanism analysis animation. This was, like he said, a 1 degree freedom type mechanism. With our particular one, the input was a linear input, so we had to decide where how long the length of this input had to be. So after we decided the length of this input, we went ahead and we had all the other information that we need to know, like the angles and the lengths of the other parts of the slider mechanism. After that, we were able to find the position of each individual piece of it, and then the velocities of the whole entire movement, and then the accelerations of the whole entire movement. One of the examples are internal combustion engines, trains, electric knives, toys, block feeders, and I'm sure there's tons of other applications out there. For our particular slider mechanism, it's sliding across. This is the input here that we were talking about. It's going from one to the other. That determines, that's what we had to find, which determines the whole entire movement of our mechanism. And then it goes in and we show you it in an internal combustion engine example, and it'll break it down and show you how it unfolds to the very basics of what we analyzed. And then David will talk about our 4-bar linkage.
4-bar linkage is another one of the simplest 1 degree of freedom mechanisms. It's made by 4 rigid links connected by 4 rotating joints or radial joints. This is the ground link. It never moves. That's the one in black. And then the others move around it. If you choose any one of these links, other links to be inputs, you can determine the positions, velocities, accelerations of everything if you know the position, velocity, and acceleration of any one input. Okay, the synthesis involved, we had 3 positions of the coupler link given, and we had to synthesize the rest of the mechanism so that our 4-bar could go through these 3 positions. The first part is to find poles A prime and pole B prime. This is just found by analyzing the positions of the 3 positions of pole A and pole B, and then you basically put those on a circle, and the center of that circle will be your pole positions. Once that's done, you have all the information you need to find the link lengths for R1, R2, R3, and R4, the 4 links. And you also will have the position, since you have A prime and B prime, you can find theta 1. This is the angle between A prime and B prime, the link that does not move. Okay, once this information is known, you can apply Grashoff's rule. This says that the longest and shortest link is less than the 2 medium links. Ours, in this case, it became true, which means we have a type 1 mechanism, and with the shortest link being the base link, that means that we have a double crank mechanism. More about this will be discussed later. We chose, for the synthesis, an input link 2, and then we determined the limits and intervals of the positions that we're going to test. We chose to do 1 full rotation of the input crank, so 360 degrees, and then we took position analysis at every one of the degrees in between, so 360 individual position analysis. Once we had that stuff, we could determine all angles and joint positions, and from that, where each location of the joints were, and we can compare that to what was given to us and make sure that our mechanism could go through all the points. Okay, this is just some of the data, all of our R values, theta 1, and then this is just the matrices used to determine position pole A and pole B. Okay, this is a chart of closure 2, because you get 2 closures when you solve for positions, and closure 2 happened to be the one that was right. You'll notice that this is the path for joint B, this is for joint A, pull A prime, pull B prime. Both of them are circular, which needs to be, and they also both go through a full 360-degree rotation, which supports Grashoff's rule that it's a double crank mechanism. And this is uniform because that's the input. You'll notice it speeds up here. There's more distance between each point on the bottom. We'll discuss that on the next slide. This is our animation of our 4-bar linkage. You'll notice that the link tumbles, especially in this quadrant right here, and that's why that joint speeds up and there's more distance between each measurement. For conclusion, some simple 4-bar mechanisms that are still used today are cabinet hinges. You can use 4-bar analysis to analyze double wishbone suspension. Tools like vice grips apply 4-bar to give you better leverage on things. This is how some of these simple mechanisms are still used today.